Hello and welcome. This is an introductory lesson to vector concepts. In this lesson, we'll try to answer questions such as, what are vectors? Why do we have to study them? And further to this, how do we use vectors to solve problems? Remember that whenever we're solving problems, especially in sciences, we're looking into various quantities working together. And for us to be able to produce a solution, we need to know two main things about these quantities. Number one, the size, which we refer to as the magnitude of each quantity. And number two, how the quantities will work together or how they will interact with one another. And vectors do a great job helping us with just that. So, for some quantities, it is sufficient enough for us to know their size. We call them quantities that are scalable, or in a single word, a scalar. Examples of scalar quantities are mass, length, temperature, area, volume. We can add more to it. Some other quantities need to be described by their size or magnitude, but also the direction, and they are called vectors. Examples of vector quantities are force, displacement, magnetic field, velocity, acceleration, etc., etc. So let's take an example of a vector quantity, the force. Suppose that we have an object that is sitting here on a flat surface. We're applying a force of, say, for example, 10 newtons. Now, this force will cause a displacement in the object. And the bigger the force, the further the object will be from the initial position. However, on the other hand, if we are not given the direction of the force, we wouldn't know if the object is going towards the right or towards the left. So in this case, for this force, we need to know not just the magnitude, but also we need to know the direction of it. And that's why we say the force is a vector quantity. In the first example, we're going to take a look at some quantities as described on this chart, and we'll describe them as scalars or vectors. And before we do that, I want us to practice this exercise on an app called GeoGebra. It's a very interesting app. And for this, we're using the lesson prepared by Mr. Peter Sassman. So, as you can see here, we have two boxes, a scalars and a vectors box, and we're going to drag each quantity into the respective box. So my guess is that the mass is a scalar. So, and as you can see here, the cross turned into a check mark. And if you try to put this into the vectors box, it's not going to work, right? So we know now it's a scalar. 5 kilometer bearing. Now I want you to guess before we move this in the respective box. So 5 kilometers, that's a magnitude. Bearing will show us direction. So I would say this is a vector. 40 degrees Celsius. So this is temperature, and temperature has no direction. So that's a scalar. Displacement. Displacement tells me where the object is, where the new location of an object is. So that should be a vector. Velocity is also a vector. It tells us the direction of the speed. Length, that's a scalar. It doesn't have direction. Acceleration has direction. So that's a vector. Energy is described by simply a single number. So that's a scalar. Speed tells us how fast we're going, just the magnitude of it. So that's a scalar. Force is a vector. Distance is a scalar, and weight is a vector. So let's go back to our little exercise here. So we said that 5 kilometer bearing, that's a vector. Temperature is a scalar. Mass is a scalar. Displacement a vector. Velocity vector. Length is a scalar. Acceleration a vector. Force is a vector. Distance is a scalar. Weight is a vector. Energy a scalar. And speed is a scalar. Now, in the next part of the lesson, we're going to take a look at how to draw a vector and how to name it. So, this is a line segment. It has two ends. One of the ends is what we call the tail. The other end is what we call the head. And in order to tell them apart, the head will have an arrow. Now, sometimes we refer to the head of the vector as the tip of the vector, which we use whichever term is easier to you. Now, the length of this line segment will describe the size of the vector, and the arrow will describe the direction of it. Now, how do we label vectors when we are solving problems? So we need to communicate that. So normally we use uppercase letters for each end. So an uppercase letter for the tail, an uppercase letter for the head. So we'll say that this would be vector AB, and to indicate that this is not just two random numbers connected to each other, we will draw the vector symbol on top of it. Now, sometimes for convenience, we use a single letter to describe a vector, and we can use any letter of the alphabet, obviously, but it is very important that when we use a single letter, we have to use a lowercase letter. So they're both representations of a vector. Now, one thing that is very, very important is that we always start reading the vector from the tail going towards the head. So the tail comes first. Now, two vectors we say are equal if they have the exact same magnitude and exact same direction. So these two are examples of two equal vectors. Two vectors we say are opposite if they have the same magnitude. So if you measure or if you look at the length of each vector, they're exactly the same, but they are opposite in direction. So here we go. So if two vectors are opposite in direction, though, they're not necessarily opposite. For example, you can see here the directions of these two vectors that I just drew are opposite, but their magnitudes are different. So that means these two vectors are not opposite vectors. So for two vectors again to be opposite, both the magnitudes must be the same and the directions must be opposite. So it doesn't work having one or the other. Now, when two vectors are opposite, such as, for example, if you call this vector AB and this one vector CD, then we'll say that vector AB is equal to negative vector CD. Similar to this, we can also say that vector CD is the opposite of vector AB. So if you are reading a problem and the problem says that you're given two opposite vectors, you would immediately know that these two vectors must have the same magnitude, okay? Now, two vectors are parallel if their directions are either same or opposite. So here are some examples. So here is one and here is another. Let me see. So these two are two parallel vectors. They're going the same direction. Magnitudes are different. They're still parallel. Here we have another set of vectors. So they go in opposite directions, but they're still parallel, right? And let's make up one more example. We have two equal vectors. They're always parallel. And two opposite vectors also are always parallel to each other. Now, another vector that must be noted is the zero vector. The zero vector is represented by a dot, and a dot has a magnitude of 0 units. And obviously a dot has no direction because you cannot point it in any way, a quantity that doesn't actually have value. So properties of zero vector is if you add a zero to a vector, just like when you add a zero to a number, then the answer will be the vector itself. Now, any vector has an opposite vector. So any vector A has an opposite vector, negative A. And if you add them together, the sum will be 0. So now we're going to take a look at this next exercise and we will describe which vectors are equal to vector AB or vector CD or vector EF. And for this, we're going to take a look again at the GeoGebra activity first. And then we'll complete the exercise on the handout. So again, this activity is produced by the same teacher, Mr. Peter Sassman. And we have a bunch of vectors, the blue vectors in here, and we want to check and see which vectors are equal to the first and which ones are the second, and we'll have to drag them accordingly. So this vector here, I'm going to put it right on top of this vector. It seems that they're equal. So there we go. Gonna try this vector here. No, it doesn't fit here. Doesn't fit. And you can tell that they're not equal. So this vector goes nowhere. Now, this vector goes upwards. So we don't have any upwards vector in here. So this doesn't fit in any of the boxes. So we have this vector in here. So let me check and see. It looks the same as the one in the middle. And I'm gonna try all of them. This one seems the same in magnitude, but it's not actually, and the direction is opposite. Doesn't fit anywhere. Let me check this one. Seems that this one belongs to the third. And here we get another one. These are kind of easy to identify when they're horizontal, right? And here we go. And it seems that we have all the answers correct. And we're going to do something similar here with the diagram, which is not exactly the same. But here I drew 3 different vectors. So vector AB, vectors AB, CD, and EF. And what we're going to do is find the vectors that are equal to each of them, each and every one of them as described. So vector AB, the way I would look at it is for the direction is like 2 to the right and 1 up. So 2 to the right and 1 up. So I don't see any. It seems that vector K is equal to vector AB. So I'll write this down here. And this one doesn't fit. This is going down, down. So it seems that that's all there is for vector AB. And wait a second, vector C2. Now for vector CD, so we have to look for horizontal vectors. So we have vector D, we have vector B, we have vector M. So we'll say vectors D, B, and M. Now last we have vector EF, which is pointing down diagonally. So 1 to the left, 1 down. So this is 1 to the right, 1 up. That doesn't work. And this one is going down. It seems that we're going 1 down and 1 to the left. So it seems that vector Q would fit there perfectly. So this one, no, but we have vector H. And then we have vector G, vector A, and yeah, G and vector A. So we have, again, just to double check, so vectors A, F, G, H, and Q. So we need to add one more, vector F. And voila, so these are the equal vectors. In the next exercise, we're given a regular hexagon. And what we want to do is give an example of vectors as described. So 2 equal vectors. Obviously, you can find more than 2 sets, but I would say vectors AB and ED are equal. It is important again, And I must emphasize, whenever we name a vector, we start from the tail and we finish with the head. Now, parallel but different in magnitudes. So vectors FA and EB are parallel. Equal in magnitude but opposite in direction. So for this, I will refer to vectors AB and DE. Equal in magnitude but not parallel. So equal in magnitude, since we're told this is a regular hexagon, so that means that each side would be the same. So we'll say, for example, vectors AB and BC. Different in both magnitude and direction. So I would continue with vector AB and then finish up with vector AE. Now, in the next exercise, we will identify vectors that whether the following statements are true or not. And the way that this works is that since we're given two equilateral triangles, ABD and EBC, equilateral means that all sides are equal, so the magnitudes of each length, each side, are the same. And we're told that vector B starts at A, ends at B. So that would be the vector AB. And then we're given vector A starts at A, ends at D. So that's vector AD. And last, vector C, which starts at E, ends at C. So EC. So for this, we're going to use again the GeoGebra app. So let's take a look again. And take things from there. So another amazing activity by Mr. Peter Sassman. Here we go. So we're going to look at BE and A. So are these two vectors the same? So again, read the vector from the tail, B, the head, E. So BE is equal to A because they're parallel. So we'll put a check mark here. Vectors CB and B. So vector CB and vector B. So they're two vectors equal in magnitude, but they point in opposite directions, so we won't put a check mark there. Vector DB, so just try to follow from D to B, whether it's equal to vector C, so they seem to go in the same direction, same magnitude. DE, so connect points D and E. That means that it's going to be parallel to the two bases, AB and BC. So that is equal to B. Vectors A and C, they have the same magnitude, but they're not equal. Magnitude of AC equals A. Well, AC is both bases of the triangle, so that's twice vector A, so we won't put a check mark there. DC, so vector DC, imagine connecting point D with C. Is that equal to C? I'm going to say no. Magnitude of C and magnitude of A. So yes, they do have completely different directions, but their magnitudes are equal. And vector AC equals 2 magnitude of C. So we're looking into the magnitude, so the direction won't matter. And AC is twice the length of the side of each triangle, which makes it equal to 2C. So if you check your answers, we did a great job in here, and we can move on with our lives. So I'm going to say that it is true that vector BE equals vector A. Vector CB and vector B, they point in opposite directions, so nothing there. Vector dB equals C. So dB and C. So they are same direction, same magnitude. Vector DE and vector B. Same direction, same magnitude. Vectors A and C. So here is A, here is C. So they're all different directions, so same magnitude, so no check mark there. So the magnitude of AC, which means the length of AC, compared to the length of A. So that's not true, they're not equal. DC and C, so here's vector DC, and here's vector C. They're not equal. Now the magnitude of AC, which is from here to here, and twice the magnitude of C, which means from here to here. So these two lengths are equal. So we're going to put a check mark here. Magnitude of C equals magnitude of A. Almost forgot this. So we're talking about their magnitudes, so just their lengths. So the lengths are the same, so I'll check mark to that. Now, the angle between vectors. It is very useful for us to understand what it means to draw the angle or to find the angle between two vectors. So we need to know how to draw it first in order to be able to solve the problem, obviously. So suppose that we have two vectors in here. So we have this vector, which I'm going to call the vector M, and this vector here, which is vector L. Now, the angle made between these two vectors is the smaller angle between them. For example, if you place two vectors tail to tail, that's how we figure out what the angle between them is. We always refer to the angle made between two vectors to the smaller one. So again, when you place two vectors tail to tail, the vectors will make two angles. This one here, the green, and the pink. But the angle that we refer to as the angle made between two vectors is always a smaller one, so it would be this acute angle. Now, here we have an example where the angle between the vectors is obtuse. So again, you place the vectors tail to tail, and the vectors will make two angles with each other, and we refer to as the angle made between two vectors to the smaller one. So here's an example of how to do this. So we have two vectors, vectors u and v. We want to find the angle between them. What we do is we place the vectors tail to tail. What I like to do usually is keep one vector where it is and then bring the other vector with the tail at the tail of the first. So in this case, I'm going to bring vector v with the tail at the tail of vector u. There we go. The angle between these two vectors will be this one here, the smaller angle. Now, very often when we solve word problems, word problems I was going to say, very often we have to deal with bearings. So what are bearings? Now, bearings are angles measured from the north light clockwise. That's the definition of it. And we use the direction lines on the compass. So here is the compass, by the way. So this would be the compass represented by these two lines. So we usually refer to, just going to make this a little bit more perfect. Here we go. So we refer to the first one here as the north line. And here is the south line. And here goes the east. And last but not least, we have the west. So we use the compass in order to describe the bearings. And whenever we actually use bearings, obviously there are different ways of using the compass. We start from the north line and we go in the clockwise direction. Now, whenever we are told that the object is moving in the northeast direction, it means that this object will go halfway between north and east. So we're going to have a 45-degree angle. Same applies to going southwest or southeast or northwest. Now, bearings, on the other hand, do not use the symbols north, east, south, and west. So bearings consist of 3 numbers. For example, if we're trying to find the bearing of this particular vector here, which can represent displacement, by the way, then we're going to say that the bearing is, again, start from the north line, move clockwise. You can see here we have 90 degrees and here we have 40. I was thinking of 130, the answer. So we say that the answer is 130 degrees, so a bearing of 130 degrees. Now, in the next example, we have the vector going in this direction. So in this case, we're going to say that the bearing is, again, you read it from the north line, move clockwise. So as you can see in here, we have 90 degrees here, another 90 in here, 90 plus 90, 180. And then we have this little angle here, which is whatever is left over from 90, take away 62. So that's like 28 degrees. So this will make the bearing equal to 180 plus 28, which is 208 degrees. Now, bearing is a convenient way of describing direction because all we have to say is the word bearing, actually, or the term we have to use is bearing and just the angle. But that's not the only way to describe direction. Another way is by using the names for each direction, so the north, south, east, and west line. So for example, we can read this direction here, described in the first example as going from east towards south. So from east, going towards south, 40 degrees. Now, very important is that we used 3 numbers to describe the angles using a compass. So we have to add the number 0 here. So east, 0, 40, south. The same vector or the same direction here can be described by using the south towards east motion. So if you go from south to east, you're moving 50 degrees. So south, 50 degrees towards east. So we have to add the 0 again. So similar to the next example, we can also say that in this case, we can describe it as going from west towards south. So from west towards south, we have to move only 62 degrees. So you write 0, 62. Or we can say from south towards west. So south towards west. We can say that we have to move 90 minus 62, that's a 28 degrees. So we write 0, 28 degrees. Now, very often the motions described in or displacement described in the problems we are about to solve will ask us to identify the angles between bearings. So how do we do that? Suppose that the ship is traveling at a bearing of 100 degrees. So remember, just by knowing the bearing, I can easily describe the direction of the ship by using the compass. So that's 90, so that would be 100 approximately. Then again, we're eyeballing it and exaggerating the diagram for the purpose of it being clear enough. So this would be the vector that describes the motion at a bearing of 100 degrees. And then it changes direction and heads south, which means that this object will go south. Now remember that if I drew this vector down here, which will describe exactly where the object is going, this will describe the south motion. So the bearing vectors will be the blue one and the pink one. But when we say to find the angle between the bearings, it means to find the angle between these two vectors. Now I want you to think, how do we identify the angle between two vectors? So remember that we have to place the vectors tail to tail. So we take this vector right here. So now the angle between the two bearings, remember this is 100 degrees, right? So the angle between the two bearings will be this angle, right? How many degrees is this? Well, this whole thing is 180. You take away 100, so that would be 80 degrees. So in this case, we're going to say that the angle between the two bearings is 80 degrees. Now, another thing I would like you to think of is this. If the object is moving south, it means that the bearing must be 180 degrees. So when you move south, right? Now, the first bearing was 100 degrees. So this is the first bearing of 100, the second bearing of 180, and then we're going to say, what was the answer again? The angle between bearings? 80. Do you see a connection between them? So you can tell that here we have 180 minus 100, which equals 80. So the angle between bearings is actually the difference between the bearings. Now, in the next example, you can practice a bearing of 260 that changes the direction west. Let's do this together. So if you would like to do this on your own, just stop the video and continue on your own, because that's fun, more fun. So I'm going to start off with 260 degree bearing, so 90, 180, and 260 means that I need to go further 80 degrees. So here we go. And then the direction is changing towards west. So in other words, the object is going this way. So the angle between the bearings now will be the angle made between these two vectors when placed tail to tail. So here goes the angle between the bearings. Now remember that this was 260 degrees. This whole thing is 270, right? So the angle between the bearings will be 10 degrees.